Good afternoon, everyone. Welcome to the CUIIC Academy and our webinar series. Hopefully you can see our first slide today. Our presentation is on high accuracy data collection to support subsurface utility engineering, locating, and other opportunities. We're joined today by Kieran Teening. The CUIIC Academy, my apologies here, I'll get that slide right. The CUIIC Academy is organized by the Canadian Underground Infrastructure Innovation Centre with the University of Alberta and Benjamin Media. The CUIIC Academy offers courses, webinars, and events to help further underground infrastructure education opportunities across Canada. Our webinar series covers a variety of pressing topics related to underground infrastructure sector. Our speakers are industry-leading professionals. We provide a monthly free educational webinar to the public, and there's a question and answer period as well. So these are put on every third Thursday of each month at 1 p.m. Eastern. And there's a full schedule of events coming up, and you can check our website there at theacademy.cuiic.ca. So I'm the moderator today. My name is Blaine Hunt. I'm a member of the CUIIC Academy and Outreach Committee. It's got some great webinars on there, and there's some great ones coming up as well. Our next webinar will be May 16th, which is on rehabilitation of manholes and underground assets. There's trench safety coming up next month as well. And there's, again, the full schedule is at theacademy.cuiic.ca. Our 2024 events coming up will be the CUIIC Advanced HDD School. So we've had a couple of these and they've been held successfully. Our next one is coming up in April in the Calgary TELUS Convention Center. And also in 2024, look forward to our geotechnical risks and consideration for underground construction workshops. So we're looking forward to this. Again, opportunities and these events will be advertised on our academycuiic.ca website. You can sign up there. It'll have all the information for you. So our 2024 webinar series sponsor is Westlake Pipe and Fittings. So thanks to them for putting these on. And we've got a great topic today. We're joined today by Kieran Teening. He's the president of TerraFlow Geomatics, and I'll let Kieran introduce himself and tell us a little bit about the presentation today.
Thank you, Blaine, and I look forward to talking to everybody throughout the presentation. So TerraFlow Geomatics, so we develop, basically, I lead the product strategy and supporting of our clients and others in the industry. So we support both above ground, at ground, and below ground data capture through our mapper line of products. And so we'll talk a little bit about some of the examples of how some of these applications are used, as well as general purposes through some of the applications and where you can see benefits through that. So the basic presentation overview and where we wanted to go with this is to talk a little bit about the subsurface utility engineering, but we're not going to focus in depth on that. But we will start with the quality levels just because it lays a bit of the groundwork as to how we think about high accuracy data capture, what it is that you want to capture, and how you might go about doing that. We'll then talk a little bit about some of the industries that have high accuracy needs and look at some of the mapping, sketching requirements for those and how you can get good quality deliverables out of your activities in the field. Take a look at some of the examples of these, the utilities, so utility features, gas mains, water mains, kind of the obvious stuff when you're thinking about utility information, both below ground, but also utility poles, wires, so on and so forth, things that you can see. You still may want to capture that and model that inside of your GIS or your CAD systems. Also take a look at different geophysical observations, following drills, directional drilling, and mapping where that drill head may go. We'll also talk a little bit about some environmental components, so looking at surface mapping, surface elevations. So if you're trying to do a three-dimensional floodplain analysis or for irrigation or septic systems, boreholes, capturing slope information. There's a lot of really interesting opportunities for this kind of technology. And when we talk about the geotechnical as well, we'll talk some about surface features, but also how you can integrate and how you can include both electromagnetic and radiation mapping, for example, so that you can couple environmental type features or environmental type readings and couple that with your high accuracy data collection and look at where you might be able to take that and how you might be able to optimize the activities in the field. So we'll then discuss a little bit about the high accuracy data collection and options, and then looking at deliverables and quality metrics. So we'll touch primarily on these points as we go through the presentation. Also, feel free if you do have any questions, please type them into the chat window. So Blaine is going to keep an eye on that, and then we will answer questions either throughout the presentation or certainly after the presentation's finished. We'll take the opportunity to answer those. So again, taking a look at some high accuracy data collection and the SU or subsurface utility engineering quality levels. And again, we're not really going to focus on that, but it does give us a sense of what you're doing, how you might look at capturing data. So, at the quality level D, type is the derived from existing records or oral recollections. And so this is really looking at, how many utilities might be on the site, what type of congestion you might have. It could look at oral histories, where the water might have flowed if you're looking at a drainage basin. So where, historical patterns of water flow, where the water lines were, so on and so forth. So again, it's not really high accuracy, but it's giving you a sense of the site you're looking at or the project that you're looking at. It certainly gives you a bit of a baseline as to what you might want to do and how you might want to capture that information. And it's always useful to have that kind of data because then it can provide that baseline so that you know what it is that you're going to be looking for or what it is that you're going to be mapping. So QLC or quality level C is really obtained by, again, surveying and plotting visible above ground features. So these are, paint marks, if in a utility locating type scenario. It could be, if you're looking at, say, oil tanks underground, you might map out the valves on the top and maybe make a presumption that it's going straight down. Maybe you couple that with engineering records to know, where those underground tanks may be based on the filling locations at a gas station, for example. And really, using that professional judgment to correlate that with the base information about the site that you have gained, either because, a gas station is going to have tanks, that, and somebody might be able to say, well, it's basically in that location. And so it's, again, adding to that confidence in the data. A quality level B then is using various geophysical methods typically to determine the existence and horizontal position of subsurface utilities. So it could be GPR, so ground penetrating radar, or looking at some of the electromagnetic tools that are provided by many of the utility locate providers, so the RICOM, the radio detection, the Viavax, Metrotex, Subsite, those kinds of tools that can help you detect some of these underground features. And again, you can't see the feature in this case. If you're using this, so you're inferring when you're doing the data collection and your high accuracy GPS, you're really inferring the location of that either by, again, GPR type tool or tracing a wire in the case of underground utility locating, and then making the presumption that that wire is attached to the utility and you traced it out properly. And so again, this often gets coupled with a verification. So in tracing, you start at a known location, you trace that out to another location, then you can come back, and confirm that you have followed the correct thing. Underground streams, you may look at inputs and outputs, or these types of things where you're inferring, but you're also validating the kind of information that you're capturing. And the quality level A is really about getting that precise horizontal and vertical location. Again, in a subsurface utility engineering, it's focused on a utility that's been daylighted, or you've potholed it so you can see it, or maybe you're doing an as-built, so before it gets covered, you're capturing that actual utility because you're looking at it. But it can also extend out to other, into other industries, into other requirements. So, maybe capturing the water line along a watershed, and a very, very precise water line over the course of any given day. We'll bring in one of those examples and talk about how that was used in ferry or tracking ferries for British Columbia to redo the dock design, because they needed to get a high accuracy map of the water levels over the course of a given year. So, just look at that, the basic, so some of the examples, locating in the one call type process for anybody in the utilities industry is would be fairly well versed in this, is primarily based for safety. So safety for the excavator, safety for anybody that's doing work on the site, as well as damage prevention. So, minimizing cost, minimizing utility strikes. There's a lot of those a year, unfortunately. And so, we paint out the marks, and it's about capturing that accurate information as to the location of the underground utilities, in a particular geographic area. So, again, using your dig area, being able to couple that with existing utility records, locating those, and then performing a scan either with GPR or looking at other visual reference points. Maybe there was no water in that area that was defined, but there's a hydrant there. And so you've got to be able to go back and think about the fact there's a hydrant, so there's got to be something that's feeding that. Even if it's an abandoned type scenario, you still need to know where those assets are. You'd still want to be able to find them so that you know what you're up against. So it's really about the safe, efficient, and effective installation, placement, and operation of all of those underground type utilities. And again, it helps for efficient and effective utilization of land, minimizing the amount that you might need to excavate, whether you can use an excavator, whether you have to hand dig, or whether you need to use something like a hydrovac service to get into that area. And then again, looking at that simple identification, the location of those underground utilities. And what are the key benefits here? If we take a look at this particular map, you have paint marks on the ground. It may be recorded in a notebook depending on where you are. In North America or around the world, the requirements are different. Some places, all you need to do is put paint on the ground, and then that locator walks away. The advantage of using a high accuracy data collection is you're now recording where that utility was. You're recording how the locator was set up, what frequency the user was on from a quality assurance and from a training perspective. And you've got validation of exactly when that data was captured, and you've got an ongoing record. And that ongoing record, we'll touch on a little bit later, can be brought back into your asset repository. So while legislatively, you may need to relocate on a 30-day window, for example, depending on your jurisdiction, you have that record that another locator could go out, find out where those hookup points were. They have the existing maps, they can validate them. They can perform the locate properly as they would, but they can, cross-reference what the prior locator has done. And it gives you that ability to keep that data, retain that data going forward. So, from a locating perspective, you've got a number of different options. And again, this applies more broadly to high accuracy data collection as well. So some of the options, at the highest level. So again, we did lowest accuracy to highest 2 slides ago. We'll go highest to lowest. But in your highest accuracy would be survey type workflows with something like a total station or a robotic total station, which is going to give you the absolute geographic positions, either based on GPS or in the case of a grid-based network based on relative positioning, relative to a survey marker, for example. And then it gives you very, very highly accurate positions, because generally you've got a fairly long loiter time, so that the unit will sit there, will collect a lot of data, and will hone in or converge in the GNSS world on that location. And usually survey type workflows are either done after you do a locate, after you do some construction, maybe a stakeout type workflow, where you do it preemptively. My apologies about that notification. Where you do it preemptively in order to stake out. And the survey type workflows give you the absolute highest of accuracies in this sense. GNSS on the pole. So again, it gives you the absolute positioning. The antenna is usually above the user. Well, generally always above the user unless you're really tall. It's typically a 2-meter range pole. It gives you very high potential accuracy, and then you could map as you're doing work. Very typical workflows for as-built data capture, for field-based data capture, if you're doing environmental type surveying, that type of thing. And it's a very good way to go about the data collection. And the key thing is the antenna is up high, and so you have minimal interference, depending on buildings, depending on the environment that you're working in, but the human or the person that's operating the system generally is not going to be in the way of the GNSS signal. The GNSS mounted on a device, is an interesting option. This is showing it on a locator, but I mean, it could be mounted to an electromagnetic sensor. It could be mounted to a radiation unit. It could be mounted to, all types of different kinds of equipment. Again, it gives you the absolute positioning. In this case, the antenna is often mounted either below the user, either inside the device or directly onto the device. So the antenna is usually below the user, gives you slightly lower potential accuracy. So the lower the antenna gets to the ground, the lower the potential accuracy is going to be. And then the interference from the body or from the person standing there is again going to be impacted. Now, the nice thing with this kind of setup, if the GNSS system is directly attached to the device that you're working with, is that you've got very high correlation between where the antenna is and what that third-party piece of equipment is that you're using to measure the utility. If you think about it on a pole mount, you have the pole that you need to keep directly vertical in order to maximize your positioning. And then you have to keep the locator or the electromagnetic unit or what have you attached to the pole or very close to the pole so that the antenna is directly on top of the feature that other tool is measuring for you. Coupling them together, gives you that very accurate positioning so that it's directly in line. And then finally, there's the relative measurements. So relative positioning, potential for high accurate capture if you're careful. But in this case, it's generally done relative to visible features. So relative to a hydrant, relative to a curb line, relative to something else. So you have to rely on that, being in place. And I say that, but in the case of a curb line, for example, if there's a road project, a road widening project, maybe they pull the sidewalks out because they're relaying sewer or doing some water work. When they relay those curbs, the alignment of the curb, the exact width of the curb, the exact placement may be different. And so if you're saying something's 5 centimeters or say 55 centimeters into the roadway based on the edge of the curb and the edge of the curb moves, then you need to go back and figure out, well, again, where is that gas main? How much did the curb move based on when that initial measurement was taken? And that's one of the key things and the key benefits of using an absolute locating or a GPS type locating scenario is no matter where the curb is, no matter where the water line is, what have you, that relative positioning, while useful, isn't required because you do have that absolute positioning of exactly where that asset is or where that thing that you're trying to map is. So you've got sort of a variety of tools. A lot of it's going to come down to how efficient does your workflow need to be? How accurate does your workflow need to be? Do you need to get millimeter level accuracy on everything? Or do you not? Can you allow for some degree of variation? And that's really going to depend on what you're measuring. And again, thinking through the kind of project that you're engaging in or that you're working on. One of the key components will be the choice of technologies, the choice of methods is going to be driven based on the accuracy that you have or the accuracy that you require going forward. So again, you've got the quality levels of how you might think about the quality of the data that you're getting, and then you've got the tools and the technologies that will give you, good positioning. The difference being is what is faster, what is slower, what is more accurate, what's less accurate. So a GNSS mounted to a device is most likely to be less accurate than a survey workflow performed properly, but it will be a lot faster to capture the data. And if millimeter level accuracy is not required, that may be a good trade-off. So again, thinking through those types of options. So taking a look just a tiny bit on the GNSS corrections deciphered. Of course, you've got the GNSS satellites, so the GPS, Baidu, GLONASS. You've got a variety of constellations of global positioning or GNSS systems that are broadcasting information. You've got a variety of antennas, be they Trimble, EOS, Bad Elf, all of which, benefits and drawbacks to everything. But you have those in the field, so that would be the rover that's doing the collection. And then usually with a high accuracy type workflow, you're going to have a correction network. So the correction networks, the three basic kinds, is a real-time kinematic. So connecting to something like a CanNet if you're in Canada, or the EOS RTK network as well. So there's a variety of correction networks that are available. There's a number in the United States, and there's a number globally, which are those sort of local on the ground. The next one is the precise point positioning type workflows, and those are the space-based. So the Trimble RTX is sort of the most popular, the high accuracy ones, but it gives you that space-based correction. Slightly less accurate than a real-time or an RTK network, slightly longer convergence time, but again, it gives you, still very good positioning, especially if you're outside of the network that a traditional RTK network. So maybe you don't have satellite service, or you're working in Northern Ontario or rural Montana or a location like that where the cell service isn't great. Normally you'll be able to get a satellite-based correction. And then there's the combination. So there's the PPP and RTK type networks where the GNSS unit or that receiver will pick up an RTK signal and will also pick up the satellite-based signal and will transfer from one to the other as it needs. So when it loses cellular connection and can't connect to the RTK, it can connect into the satellite-based. So one project that we did recently, which actually was an interesting conundrum, is we were involved in a project in the Arctic, up north of Iqaluit and on Baffin Island and places like that. And again, getting back to the prior slides around the technologies that are available, that far north, there's no service or almost no service for GPS or any of the GNSS systems. And there's almost no service, if any at all, even for the precise point positioning, and there is no RTK network. And so in that case, we did have to get high accuracy data collection. The only choice was survey type workflows in order to measure where those poles were. So we had built forms to be able to capture the information about the pole, the serial number, all of that. And then we had survey teams, or the client had survey teams that went out and surveyed the poles and captured the serial numbers off the poles, or the pole identifier, in order to pull the attribute information around the pole conditions with the poles. So in this case, they didn't need millimeter accurate, but they wanted to get within about 10 centimeters of that pole. But because there was no correction network up there, the only option available to us, or the most effective option available to us, was a survey style workflow because, based on control points, because they didn't have another option available to them. So from a purely business case perspective, there's a number of different ways to think about high accuracy data collection. We'll use utility locates as an example here, but there's a number of another number of field-based workflows that we could look at. So in a utility locate perspective, you have a ticket request that comes in. So that's the reason you're out in the field doing the locate or doing the project. If it's a irrigation or a septic job, for example, again, there's a reason to be out there. We'll call it a ticket. You perform the locate, you perform the measurements as you were by hand. So you do your scans, you paint your marks, you put your stakes in, you put your flags in, whatever it happens to be. You would then grab the measuring wheel or a laser to start measuring offsets. And then in most cases, there's a map that needs to be delivered. So in locating, there's generally a sketch that needs to be delivered. If we're looking at an irrigation job or hydrology, there's a map that needs to be output so that somebody back in the office can do something with the information that field person collected. So they would manually sketch out the map, they then submit the map or submit the sketch, and then they close the ticket. So that task in the field is complete, and usually you end up with a paper map or you end up with a drawing. Everything is relative, everything's being manually measured. So from a user perspective, they've gone out, they've had to measure everything. They've then had to walk the site several times to collect the measurements, and then they've had to draw it in. And hopefully they haven't, transposed information incorrectly or anything like that. So looking at an automated method, and again, with a high accuracy data collection, this extends well beyond locating. This just happens to be this example. Again, the ticket request, that hasn't changed. You locate and capture data. So while you're doing the locate, while you're doing the site investigation in an environmental, cleanup type scenario, you're doing the site investigation, you can capture the data at the same time. Maybe there's little pockets of pollution, there's spill sites. You can see the spill on the ground. Maybe you need to map that out at the same time. So you can do that while you're doing your investigation. And then you can generate those maps automatically. So that data could come back in and you could generate that sketch, you could generate that map automatically, and you have a digital record of all of that information. You close the ticket, and then you end up with raw data, you end up with CAD files, you end up with the ability to have GIS files. There's a lot of data output that comes out of that individual in the field doing that in-field type work. And again, it's a lot faster. It can be a lot safer. You spend less time, on the field, so you can optimize your field time. If you do have to get into traffic or in a railway, for example, if you're doing work for, again, I'm based in Ontario, so I'll use some of those examples, Metrolinx. You have to say 8 weeks in advance that you need access to the rail corridor, and then you need to pay flaggers in order to manage that process. So when you're in that corridor, you want to make sure you get everything that you can, and you want to minimize the amount of time that you're in the corridor. So you want to optimize what you can capture when you're in there, and you want to do it as quickly as possible. And again, a lot of that is going to come down to both efficiency, but it's also going to come down to safety in the site, or safety of your field staff while they're out in the field. So one thing around utility sketching. So again, this can apply to a variety of things. So utility in Ontario, there is a requirement, and in many jurisdictions in Canada, there is a requirement for utility sketching and utility sketches that come directly from the locator. So the user can go out, they can perform their locate, they can do their work, and then they have to sit down usually with a locate package or Visio or a tool like that, and they need to draw out the site. So they need to draw on the curb lines, they need to draw on the hydrants, the park benches, whatever they use for those offset measurements or those dimension measurements. And then they have to draw in all of the utilities, all the valve boxes, everything that they've seen out there that needs to be documented as part of that locate. And then they've got to do it for the dig area, that excavation area specifically. So if you can couple this with a high accuracy data collection, you can get all that information. That information comes back in. Your sketch is already 90% done because you've got all of the utility data. You have the valves, the hydrants, all of that sort of street furniture available to you because you've captured it in the field. You have a permanent record of it or a digital record of that data now as well. And then things like measurements, you can just simply click on one point, click on another, and then it does all of your auto dimensioning. So, if you've had to step out in the roadway and maybe you don't have traffic control, because many locate contracts don't have traffic control associated with them, that locator needs to go out, they need to get that valve box or that valve or the traffic loop. And So they do it once, they capture that data, and then they get the curb lines, and then they can just do the dimensioning. They don't have to go back into the roadway with the measuring wheel in order to perform those measurements. So again, you can optimize that damage prevention, but you can also optimize the time in the field and the safety of that user. So thinking about irrigation, thinking about any type of map making, if you can capture that data while you're there, and you can start doing almost, sort of the pre-drawings with all the measurements that get associated, all those types of engineering kind of workflows with this. So, if you think about installing a septic bed, you can measure off from the property boundaries if you captured them. So exactly where that bed needs to be installed, what soils need to be moved, and you can mark all of that up with tools like this, especially after you've captured the data. And then if you realize you forgot to take a measurement while you're in the field, well, you can just take it at that point at a later date. You don't need to go back and revisit the site as long as you've captured all of that information that's associated with it. So taking a look at some other data products. So again, CAD, if you've captured that data accurately, and if you've captured the data with a high accuracy system, you can output the data into computer-aided design packages. So for any design, any construction work, things like that. So it can support the field layout and accurate mapping of any known features, any locations. So if you think about a pre-site visit, that data can come back into the engineering teams with the design team, who can then design out the site, who can then provide that information back to the field team when it's time to do stakeout. So again, usually with a survey type tool, but they could provide that information back out. And then you can integrate it with Civil 3D, you can integrate it with other infrastructure design software and create your pre-design, your design, and then your as-built records, all in one seamless workflow. And you can see what the differences are between that pre-design, the initial site capture. You can see the development of the site, and you can track what work is happening over the course of time. So from a records management perspective, from a progress perspective during construction, you can see all of that data coming in, leveraging these kinds of tools, because you know precisely how far that pipe has been installed. For example, if we're looking at a gas pipe installation, you can map out the pipe as it's being built, as it's being covered. And so, one of the requirements is that you have to cover over that pipe at the end of a workday. You don't leave it exposed. So you can capture that data and you have the progress marker. So every night you can see exactly what the teams are doing. You can also integrate this with GIS type systems. So Esri, QGIS, MapInfo, depending on what it is that you use. If you're in North America, most likely Esri. But it will give you that digitized model of the real world, and that data can flow directly in from a high accuracy system in the software that gets coupled with it, whether you're using TerraFlow, Esri Field Maps, EOS Locate, depending on what it is that you're working with. You can bring that data in, and you can, they work differently, different mechanisms, but you can source that data and you can bring it into a GIS system. So you can bring that locate data into the record system, you can bring your as-built data into the record system, and then you can optimize that handoff to your designers, you can optimize that handoff to your records technicians, depending on how your team is organized. And then you've got an excellent visual of the entire service territory, or an excellent visual of, in the case of a watershed study, of what that watershed looks like, where the streams are, where the points of pollution are. So if you're looking at the point source pollution in a watershed versus a non-point source pollution, so, a sewer outlet would be a point source pollution, or a farm. Maybe there's a chicken farm and you've got runoff coming off the chicken farm. So that would be a non-point source. Basically where it is, and sort of as it's funneling in to the watershed. So you can map out pollutants, and then you can map out where they're moving through space, and also through time. You can, measure these over a period of time as well. So, it gives you a lot of opportunities. And one of the key things is building out those data products and thinking about those data products as you go and what's useful. So in this case, just talking about a couple of different examples. This one's an interesting one. So this is surface management type workflow in landfills. So if you think about it as a cut fill processing, could apply to roadworks. It could apply to anything where an excavator either has to dig down to a certain level or fill to a certain level. So in this case, for surface management, they're looking at the collection and management of surface height versus design height in a landfill. So they can also collect all the surface data, wellhead data, sample locations, and other types of information. But if you think about a landfill workflow, is you've got a space, and then you're bringing in waste, and that waste is allowed to get to a certain height. You have height requirements, you have angle requirements as that landfill is filled. So using high accuracy GNSS systems, you can optimize where the waste is placed, and you can ensure that you get up to that fill height without going over. If you go over, there are regulatory issues, there could be fines, they're relatively minor. You have huge costs involved in moving the fill to bring yourself back into compliance. If you're doing, if you're surveying after the fact, maybe 6 months later, you could have thousands of tons of material that you then have to move. So aside from the cost savings, you also have carbon issues, fuel costs, manpower or person power costs associated with it. So in this case, this particular system or this particular example is used by a company called Secure Energy, and they're looking at giving us millions of dollars in savings, specifically because they never get out of compliance. They can fill the landfill to the design, and then they can move to another cell. They can place fill somewhere else in the landfill, but they're never out of compliance. And the big thing is they never have to move. There's no unnecessary waste relocation. So the fuel, the people, they can reduce the amount that they're spending. And again, in the era of climate change, you're also reducing the amount of carbon output. Bulldozers and this type of equipment consumes a lot of fuel. And so being able to map in real time where they are relative to that design minimizes the fuel cost. You could turn it around, look at roadworks, managing the blade and the blade angles. We've all seen the GPS on the bulldozers, mapping, or the excavators mapping exactly where that blade is to ensure that as they're moving material, they're moving it exactly where the designers want it to be and the design engineers want it to be. And so when they're finished, they may still go back and resurvey just to make sure they're absolutely correct, but the odds of having to move any substantive amount of material goes down. This one's an interesting one. So this is automated data collection using radiation sensors, and there are crews that are using this for electromagnetic sensors as well, where they attach a radiation meter directly to the range pole in this case, and they've got a high accuracy GNSS that's associated with it, and then they can survey a site for gamma readings. So you get the field readout of the gamma values, you can see where there's high locations, low locations, but that ability to bring in that third-party sensor with your high accuracy GNSS, that you could build a very accurate map. In this case, it's gamma readings out west. There are crews that are working with this with electromagnetic sensors, looking for abandoned oil and gas wells, and you can map this information very, very precisely, and then you can work out your plan as to what you need to do. There's cases of this where this technology is running in the United States, nuclear plant decommissioning projects. And so they scan and they rescan, and as they're rehabilitating a site, as they're decommissioning these plants, you have live gamma readings that are coming directly into your GIS system. You can then apply whatever statistical analysis that you need to apply very, very quickly. So basically, field data capture right to the office, and then while that person's on site, they can, the office staff, the analysts can look at the data, and maybe they need to direct the technician back to a certain area, recapture something, delineate something else. You can now do that because you've got that live feedback with this kind of technology. So this is just a little statement here, which really helped speed up the data capture. Utility poles, same idea. High accuracy GNSS, where the poles are, how long the wires are between those poles, being able to do wire sag calculations. If you're looking at clearance type workflows, maybe you need to go out and map out a bunch of poles, map out the sag because you're moving a piece of equipment through the area that has clearance issues, and so you need to make sure that it's going to get underneath the wires so that you don't have to relocate infrastructure, or at least if you do have to relocate the infrastructure, you can do it before you get into the scenario where you have a problem and it becomes an emergency. You can pre-plan this kind of information. And again, if you captured it all with high accuracy GNSS, usually in this case coupled with a third-party laser, then you can capture this data preemptively and then ensure that you've got a safe work zone. This is an interesting example, getting back to the ferries and getting back to water. So BC Ferries is electrifying their ferry fleet, and what they needed to know was the water levels of where the ferries were operating over the course of a year, because for the electrification process, they were purchasing new ferries, which meant they had to rebuild the ferry docks. And so they mounted high accuracy GPS to the ferry. And so they could track over the course of a year how high the ferry got, how low the ferry got, how lateral movements left to right as the ferry was going through its day-to-day operations. And then when they were looking at the ferry dock design, they could optimize that because they had a year's worth of data and the extremes of exactly how low the water ever got, how high it got, and the movement. They could optimize the dock so that it was compatible with the ferry as it was coming into that location. So it was a really interesting project to work on and to help out with. Septic design, so we talked about this briefly a little bit earlier, but capturing the boundary information, capturing elevation. One of the key things about high accuracy GNSS is you have the XY, but you also have the Z. So you can capture the elevation, so you can optimize, so you can design for the flow. And again, you can minimize excavation, you can minimize the soil movement, you can minimize the ground disturbance, the amount of time you need to be on site, and you can move the material that you need to move, and only the material that you need to move in order to install whatever it is that you're looking to install. Or in the case of, septic or any pollution for water, you can minimize the boundary, and you can ensure that maybe the water moves a little bit more slowly through the substrate because you understand the elevation, you understand the slopes, because you've captured that data before you started doing the work. And then, of course, you can capture it after the fact to make sure that it's in compliance. So, one of the key things around high accuracy data capture is, yes, the ability to capture the data to optimize the field work, but almost as important, or maybe more important, depending on your perspective, is that data can be captured quickly. You can map while you're out there, and then you can derive a whole variety of information products. It's not just a paper map. You've got CAD data, you've got GIS data, you can have sketch information with dimension lines, you can have raw data that you're pulling in from the field. And so given that data, there's a lot of value add, there's a lot of benefit to having that kind of information. And the higher accuracy it is, the more reliable that data is for future decision making that you or your organizations may go through. So I think that's it. If any questions, Blaine? Anything that has come up, or anything that you'd like to touch on or add to in the presentation?
Yeah, thanks very much, Kieran. We do have a couple of questions here. That was really good. We're a little bit running into the hour, but we've got a bit of time for some of the questions. So one of the questions that came in is a good one about, Kieran, you were discussing the different quality levels in terms of the GNS and the data pickup. I think one of the slides you had was the sort of high accuracy data collection survey through to relative measurements, the GNS pole mount and device mount. Mm-hmm. What are the costs between those various levels of accuracy?
Oh, that's an excellent question. I'll
thank Gideon from the city of Vaughan for that, by the way. It wasn't from me.
Yeah. I'm gonna go with the great cop out of the "it depends."
Maybe there's a relative cost in terms of moving
Yeah,
from traditional survey through to some of the high accuracy data collection that's either pole
yeah.
or surface mounted. What kind of ranges could you get?
I mean, if you're taking a look at, I'm not sure what a total station costs at this point on the market, but usually, I would say at the low end, probably 10 to 20, high end could be 50 or $60,000 for the equipment. You've got the really high accuracy, with tilt enabled sensors and something like a triple R12i, which is quite costly. But you have tremendous benefit with that as well. Some of the software for that is a little bit more complex, so your user costs will go up. I shouldn't say the user, but the operator costs. So really understanding the survey workflows, really understanding how to perform a survey and how the equipment operates, down to, pole mounted or locator mounted. Again, you can usually deploy those with your regular staff, so your locate staff who are already doing the work. And in that case, you're talking antennas that are usually in the several hundreds to low couple $1,000s. And where your cost is going to be is the correction sources. So depending on the correction provider, that's usually going to be in the order of a few thousand a year per user. Again, but it depends on who your correction provider is and where you are. I don't know if that helped, if that really answered the question. I know sort of a bunch of, the key people to talk to are the vendors of that kind of equipment, as to, getting quotes and that type of thing for them.
Yep, well, that's very good. Another good question here about drones and maybe how I got to sort of interpret this a little bit to see. You've been talking about high accuracy data collection. How does a drone fit into that sort of conversation you've been having with us today?
Yeah, very well. I mean, I will admit, I don't have a huge amount of experience with drone data capture. I know there's a lot of work going on looking at drones and collecting that kind of information. Generally, the kinds of use cases that I've seen with it tend to be, surface mapping. So if you're trying to do various elevations, I know in the case of the landfills, they do drone surveys for compliance every single year. So they'll fly the landfills and remap it just to make sure that there's a final compliance check as part of their reporting requirements. In the case of underground type detection, they don't work very well, but in the case of areas where you might not have access to it, so, out over a lake bed, for example, maybe you're mapping the water line around an entire lake, it could be a very effective way if you can tell the difference between the water and the rock and where that intersection happens to be. The other, which we really didn't talk about, but to expand on, is LiDAR. And using LiDAR type equipment for pole data capture. Again, very, very fast, very effective way of capturing an enormous amount of information. The issues you tend to get into there are around access or being able to see, what it is that you've captured. So you'll see a lot of LiDAR being used, which is kind of drone-ish, I guess, in a sense, for utility pole type workflows. And that works very effectively if you can see the poles and if the LiDAR has a clear line of sight to them. And then you often get into a scenario of using another product in order to get into people's backyards. If there's a tree in front of the pole, some of the stuff's going to be missed. And so you have to go back out and capture that data. Hopefully that helped.
Good. That was from Ahmed over at Associate Engineering. And there's a question here from Dylan from Sturgeon County. So they're currently using GIS as their main information for source and record keeping. They're looking for recommendations from how does high accuracy data collection fit with their current process, in terms of, what for counties and municipalities, where do you see some of that information sort of helping them out?
Yeah. I mean, from a current process, I don't know your existing processes, obviously, but if we look at a typical municipal type process, in many cases, a lot of it is updating records information. A lot of it is about improving the quality of your records, especially in older towns. A lot of those, the pipes that were put in place, that data was initially captured by the installer on a sheet of paper. or relative to sidewalks, relative to edges of road, which may have moved. And so you've got a good relative sense of where those pipes are. And so looking at, a higher accuracy capture, in a lot of cases, it's about increasing the accuracy of your underlying network and increasing your confidence in your underlying information or your underlying records. From an as-builting perspective, really handy before something goes into the ground and before it's covered up, capture that data. And then you don't have to worry about that. You've got a really, really good record at the time of capture of exactly where that is, or at the time of construction where that is, especially in municipal type workflows. As far as how you would initially determine the location, again, it's the site visits, it's the understanding your existing records. There's a water line down there somewhere. It makes sense because you've got that in your existing record. You may not know precisely where it is. And then the selection of tools, GPR is great, especially for things that can't be traced. So concrete, plastic, things that you cannot put an electrical signal through. And maybe they were installed prior to having a tracer wire. But again, they're limited. GPR is limited because it's only going to go so deep. So if you look at some sewer, you may not be able to get that deep. Electromagnetic locators, same types of issues. So all of this technology is something, the technological landscape out there is absolutely phenomenal. And the kinds of tools that are available are absolutely phenomenal. But they all have benefits and drawbacks. And so it's really on a site-by-site basis. GPR is a great tool, but it's not going to solve every problem. Electromagnetic, same thing, great tool, but it won't solve every problem. So usually it's a couple, it's coupling those tools together to figure out, what's ideal. Hopefully I answered the question.
Yeah, no, that's very good. I'll add in there as well. There are some standards that are out there for municipalities in terms of as-built. So you touched on it. There's a CSA S250 and an ASC 75 that really discuss sort of as utilities are being installed, how to map them. It gives you some, as you touched on there, some various degrees of accuracy, and those will have relative costs as well. A comment here from Mohammed over at Colsall. Excellent presentation. The equipment for high accuracy data collection must be expensive, but probably benefits it has with time savings, damage to the property. Is it worth considering for projects? Sorry, it is worth considering for projects requiring high accuracy. So a great comment there from Mohammed as well. I'm going to leave that there. I think we're done questions at the moment. Just going to cycle through. Thanks again to Kieran for a great presentation. Some great thoughts and touched on a lot of different areas that I think our members might touch on. If you are not a member of CUIIC, please check us out. And there's some great benefits. I'll leave that slide up there. If you could read it, your eyes would be better than mine, but we do have an extensive list of CUIIC members. One of the questions that came out were the webinar costs. These are free currently on the website to CUIIC members and non-members. So we're leaving it out there as a benefit for all the people that are interested. CUIIC is very much committed to trying advancing some of the education in this industry. So thanks very much to our members for their time and commitment. And Kieran, thank you today for this presentation. It was a lot to think about. That's great.
Thank you for having me.